The machine learning is better mastered through practice. So the more you practice, try to apply what you've learned to real life scenarios, try to see how it's going to work. That really is a very good way to become to master machine learning in a proper way. So that's what we're going to hold with. After this class, a couple of 1 or 2 sessions now, we're going to have a couple of practical demonstration and discussion on how you can pick a problem in your own area, and then try to see how you can make use of machine learning to solve it. So, however, today we are going to look into Naïve Bayes, which is among the group of classifiers that are often regarded as simple. Or being simple doesn't mean they cannot do wonders. Sometimes, especially depending on the data set. Naïve Bayes classifier is especially good for when you have to do with text classification, as we're going to see later, because it has to do with computing probabilities, and try to see the likelihood and then the procedure, probability and related stuffs. These are some of the bases. So we're going to look into Naïve Bayes classifier. So what is Naïve Bayes and how Naïve Bayes work? And then we look at examples, and then we're going to consider the pros and the cons of this very popular simple machine learning algorithm. Before we move on, I would like to clarify. You see, this Naïve Bayes, naive, that is something, when you say something, somebody is naive, that is it's really inexperienced or very simple, because the classical Bayesian network or Bayesian theorem, as we are going to see it, is very complicated. It assumes that every variable is dependent on each other. For example, if you give me a kind of X1, I have predictors, or like we call features or attributes. We have X1, X2, X3, X4. So when you want to use the classical Bayes theorem, so you have to look at, okay, what's going to be the effect of this on this? See, X1 given X2, then X1 given X2, X3, X1 given X4. You have to look at a lot of conditional probability, which makes the classical Bayesian theorem to be intractable. We say it is intractable in computing. Intractable. It means it cannot be computed within the available resources we have presently. Because especially when you have a huge number of attributes, and you have to consider this condition upon this condition upon this. So it doesn't work. So the one that is working is people have to assume that let us assume that X1 does not depend on X2, X2 also doesn't depend on X1. They are not affecting each other. We call it the independent assumption. Independence assumption. That's it. We want to assume that the predictors are not affecting each other, which in reality actually is not correct. In reality, so you can have X1, X2, X3. Sometimes you use only X1, you don't get good results. Use X3, you don't get good result. You use the 3, you don't have very good result. But when you use X2 and X3 only together, you have good result. When you bring X1 and X2 also, you also have good result. Because it depends on kind of the relationship, the dependency among them. See, even in real life, there are friends, when they're together in a particular project, they work very excellently well. However, there are another group of people, although they are not enemy, they are friends, but they always joke too much. If you give them tasks and you put them on the same group, they're not going to achieve something reasonable because of excessive jokes or whatever play they engage in. So in that case, we look for two people, when we put them together, can they really work together professionally and achieve something reasonable? So similarly, when we have predictors, when we have different variables, few variables are more related to one another and they affect each other in different ways. However, the classical, the normal Bayes theorem, if you assume that particular tendency, then when you assume the dependency among each participating attributes, that x1, x2, x3, they are dependent, then in that case, we are going to have a very wide and long probability distribution to be solved, which is not supported presently in terms of, we call it intractable. You can solve it in reasonable time. That is the computational time complexity is too much than what can be beared. So what do we do in this case? We now assume that x1, x2, x3, they are independent of each other. So whatever probability we're going to compute, we compute it irrespective of the dependency. This is where the name Naïve came actually from. It means it's a special type of Bayesian classifier that is making that kind of very simplistic assumption that, okay, just take them as variables that are not affecting each other. Now, so I said we're going to look at this is just telling us a brief kind of background about where the name came from. So original one is the Bayesian classifier or the Bayesian theorem, as we're going to see it. So what is Naïve classifier? How does it work? Then we look at examples and we go. So in Bayes classification, it is worth to mention that it's a statistical classifier which performs probabilistic prediction. That is, it predicts the class membership probabilities. So when you have a particular sample, it will predict the probability that this sample belongs to, let's say you have two classes, even many classes. Actually, one of the strong points here is you can use it for many classes. It's very powerful at that. You only need to calculate the probability of this sample belonging to each of those classes, and then you assign the one that achieved the highest probability. You assign it to that particular sample. So, of course, the rule of probability always there. Addition of all the probability cannot be greater than 1. So you are going to see, we're going to have example as we move on. So the foundation assumption is based on what is popularly known as the Bayes theorem. So our mathematicians in the house, so you can be a witness to that. So Bayes theorem is very popular. Comes to probability solutions. So as for performance, we say that a simple Bayesian classifier, which we call Naïve Bayesian classifier, has comparable performance with decision tree and selected neural network classifier. Pay attention to that, selected, you know? So once the data is getting complicated in some area, Naïve Bayes might not be able to solve it. Why? Because of that assumption that there is independence among the variables, which in reality, it doesn't hold. See, there are always dependency among variables. You can have x1, x2, and x3. They are closely related. When you put them together, they can work together cooperatively to achieve better results. However, Bayes network, Naïve Bayes said, no, we don't want to deal with that. Not because we just want to do that, because the classical Bayes theorem is complicated and you can't solve it with the available computational resources as at present. We call such problem intractable problem. Now, so, however, the Naïve Bayes now made, okay, since Bayes theorem is a very nice idea, so though complicated at the moment, so at least let's create a simple one out of it. This is what we call it. Naïve Bayes is a simpler version of Bayesian classifier. However, as simple as it has been proven that it has comparable performance when you compare them to decision tree and selected neural network. Neural network is one of the very foremost also algorithm that we're going to look into later, inshallah. So, and also it depends on the data sets, and they are especially very useful when you are dealing with text classification. We are not saying they are the best in text classification, but based on experiences when it comes to text classification, because some of the natural language processing where we process text, even voices, they are often based on probability. Most of the models that are often used, they are probability oriented. and they do perform really excellently well. Now, another unique attribute we have to know when we talk about Bayes classification is that it has an incremental property. What do we mean by this? That is, each training example can incrementally increase or decrease the probability that a hypothesis is correct. See, what we are seeing in essence is, as you know, that if you calculate probability of an event, let's say we have 5 samples, and you want to calculate probability that in these 5 samples, there are 2 yes, and there are 3 no. So you want to calculate the probability. If I pick 1 yes here, if I pick 1 sample, what's the probability that that sample is a yes? That's going to be 2 out of 5. You see? Now, if I increase, this is the meaning of incremental properties of Bayes classification. Now, if I increase the sample to become 6, you see, if the sample now becomes 6, I have to go back and recompute the probability because it's going to change. You see, let's say we added 1 new sample, and that sample now happened to be another yes, which means our yes is going to become 3 out of 6. This one by incremental. That is, each additional training example, we incrementally increase or decrease the probability of a particular hypothesis. You see, so before, this probability of no used to be 3 out of 5, which is higher, but now it's going to be 3 out of 6. Although it increased, the addition of 1 sample increased the probability of yes, because it increased from 2 over 5 to become 3 over 5, which is an increment, 3 over 6. However, for that, the second class, it actually reduced from being 3 over 5 to becoming lesser, which is now 3 over 6. That is what we mean by incremental. That is, each training example added can incrementally increase or decrease the probability that an hypothesis is correct. Now, also, as for the standard, even when Bayesian methods are computationally intractable, this is what I've explained. You see, the classical Bayesian method, they are computationally intractable. They can provide a standard of optimal decision making against which other method can be measured. So that is why, due to some of the unique attributes of Bayesian techniques, people cannot just do away with it. It has the intractability, which there's no way you can deal with that for now. So rather than throwing it away totally, they say, okay, let's make an assumption that the variables are not dependent, because the dependency is what made it to become intractable. So let's make an assumption that it's not dependent, they are not dependent on each other, which I said in reality is not correct. This is one of the weakness of Naïve Bayes classification techniques. It makes an assumption that we know that it's not correct, but there's nothing we can do. That is the best we can offer as far as it is concerned for now. Now, so moving further with Naïve Bayes, we mentioned earlier that it's based on Bayes' theorem. And what is Bayes' theorem? This is the Bayes' theorem, which tells us that the procedural probability of a class, the target class we want to predict, given predictor attributes, given the predictor that you want to use, is given with this formula, which is 1 is probability of X given C, that is P of X given C, which is the prior probability of predictor, provided that K is going to be C. That is what is class 1. C is going to be, we can have class 1, we can have class 2. Let's say we are dealing with 2 classes or 3 classes. It doesn't matter. So what is the probability of this particular predictor being given? Probability of the predictor, given that the class is maybe 1, 2, or the second one. And the probability of the class, each of the class, divided by the probability of the predictor itself. So when you expand this, so we're going to have something like P of C given X, which is now expanded to be P of X1 given C, that is each of the probability. See, X1 given C, X2 given C, up to the end. So if you want to go with the Bayes theorem, then we have the independent assumption that, okay, this is not dependent on each other. We make our life very easy, as we are going to see in the computation of the probability becomes very easier. Now, so we said the Naïve Bayesian classifier, which is based on the Bayes theorem with independence assumption between predictors. This is the simple secret behind Naïve Bayes. It has independent assumption between predictors. It means deal with X1 independent of X2, just assume that they are not affecting each other, which in reality they do affect, but there's nothing we can do. Now, so in Naïve Bayesian models, it's easy to build with no complicated iterative parameter estimation, which make it particularly useful for very large data set. So because of that huge assumption that we just kick out something very, very important, and it do work actually. That is why in life, when you try to solve some problem using some very powerful system, if it doesn't work for you, try a very simple one. Maybe it could work. And that's what was actually tried out in the case of Naïve Bayesian classifier. Now, so, and it became one of the very simple classifier, very fast, even when your data is big, when the number of classes is big, you'll still be very fast because you just need to calculate the probability easily. You can fix in the values. Despite its simplicity, we said that Naïve Bayesian classifier often does surprisingly well, and it's widely used because it often outperforms more sophisticated classification algorithms. So sometimes, just like remember what I used to tell us, the principle of let the data speak. Let the data speak. So whenever you have a new data set you want to use, my advice usually for my students is start with KNN's neighbor, Naïve Bayes, see what you can get, then decision tree, before you start going to big guys, like neural networks, supervector machine, and host of other methods. Because these simple ones will easily get you results, and they are easily explainable to your client easily. You can easily explain to your client. Your client can easily understand it. Even you also can easily understand the way it works. So unlike the other group of classifiers that we are going to deal with later, where you have to go into some deep theoretical mathematical computation. Now, how Naïve Bayesian work? How does it work? What is the simple procedure? We can summarize the procedure into three. So the first step is to convert the data set into a frequency table. Remember when we discussed decision tree, we also mentioned frequency table, something similar. So you have to first of all convert the data set into frequency table. That is, check it and see how many times does this happen, how many times does this happen, because you are going to calculate the probability. So once you are done with that, then step two, create likelihood table by finding the probabilities. See, you create likelihood table by finding the probabilities. And then step three, you now use the Naïve Bayesian equation to calculate the posterior probability for each class. So using the Naïve Bayesian equation, which is the equation that has been simplified by assuming that independence does not hold. Now, so use that particular simple equation now to calculate the posterior probability for each class, no matter the number of classes. Like I said, this is one of the strong points here for Naïve Bayes. So let's say we're dealing with two classes or three classes or more. So you have to calculate the posterior probability for each class. So therefore, the class with the highest posterior probability is the outcome of the prediction. So if this one is having 0.5 as the probability, this one is having 0.3, and this is 0.2, of course, the rule of probability always holds. You can't have probability that is more than one when you add them together. So we are going to assign that sample to the class that has this highest. Let's say this is class 1, class 2, class 3. So this sample that has this particular outcome of posterior probability will be assigned to class 1 because it has the highest value of probability. So those are the three simple steps that you go through when you create the Bayesian. So the real work is when you create the frequency table and also when you create the likelihood table, which is once your frequency table, that's why you pay attention to the frequency table. Because if your frequency table is wrong, that means your likelihood table is going to be wrong. And everything you do after that is going to be wrong. See? So that's why someone need to pay very much attention to everything you do. Make sure the frequency table is correct. Then that will make sure also that your likelihood table is correct. And then whatever probability you calculate is going to be correct. Now, those are the 3 simple steps you take in it. Now, let's look at an example. So something similar to the example we took in the case of decision tree. Now, here is a problem to be solved. We want to decide if people should go and play golf or not, depending on the weather condition. So we have the first attribute, we have the outlook, we have the temperature, we have humidity, we have windy, so windiness or otherwise of the weather. Then we have the decision. This is our class. So from here, you can know the number of classes you are dealing with. From here, you can know the number of classes you are dealing with. Here now, I can see here, you can see no, no, yes, yes, yes. So we have only 2 classes now, 2 classes. And like I said, it can be as many classes as possible. And Bayes, Naïve Bayes is very good at that. So just calculate the probability and then you assign it to which one are the highest probability. Now let's take it. The first step is to create frequency tables. You create frequency tables, which is you look into each of the attributes, bring this one out. You have outlook. What are the values possible in the outlook? You have rainy, you have overcast, or then you have sunny. See? So, and then you have it here, play golf, which is yes or no. So now tell us when it is rainy. Let's start from sunny. When it is sunny, okay, how many sunny cases do you have that the outcome is yes? This is 1. This is 2. Sunny, this is no, another side. You have to check that one. This is 1. This is no. You can see here, I can identify 3. There are 3 cases whereby the attribute outlook has value sunny, and it is yes, 3, and then it is no. No. So we have 3 cases where the attribute sunny has yes, do play golf. And then another 2 cases where it said no. So you fix it in. You have that was sunny 3, 2. The same principle, you check overcast. See where you have overcast as value for outlook. It seems they always say overcast always return yes. Overcast always return yes. This is how you prepare your frequency table one by one. So our frequency table so that whenever it's overcast, you have yes. No is 0. Then you go to rainy. The same procedure, fix into. It is rainy here. This is no, no. Okay, anywhere it's rainy, no. There's a rainy air that is underside, yes. Rainy is yes, making 2. See, so you are going to have 2 against 3. So we are done with frequency table for the outlook. You move on to temperature. You do the same thing for temperature. Check one after the other the values of temperature, hot, mild, and cool. Then assign them appropriately. Go to humidity. We have only high and normal in humidity. Assign it also appropriately. And also go to windy. Then we have exactly like this. Now, so these are the frequency tables for all the variables. Now, once the frequency table is done, then you move to the next step, which is to calculate the likelihood. See, now you need to calculate the likelihood of used from the frequency table. So you take it one by one. See, you take it one by one. Let's take the outlook case. See, we already had the frequency table there. Now let's calculate the likelihood. So, here now you are going to check what is the probability of playing golf. See, probability of playing golf. Sorry, when it is sunny. If it is sunny, playing golf will be 3 out of 9. Otherwise, yeah, because how? Because yes, pay attention to this. Well, this is probability. See, here you have play. Let's go back and do something. If you count the number of If you count the number of yes and no, you see that they are splitted into 9 and 5. I think I'm correct. Yes, it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So yes is 9, and the other one is just 5. So now under yes, Sunny and yes is 3 out of 9 because you have 3 here. And you see the total here, by the way. You see the total here. You can easily see the total. See, and there are ways you can easily cross-check. For this one, Sunny, you have 5. For Overcast, you have 4. For Rainy, you have 5. If you add them together, you must get the same value here. The total air across must be equal to the total air. Otherwise, your frequency table is not correct. You quickly go back and check where you made mistake. This is one way to double check when you are dealing with Naïve Bayes or any frequency table-based system. So the sum of everything horizontally will add up to make the total here. If you also add them off vertically, then you're going to have the same value. That shows that, okay, everything looks good. So now, so to calculate the likelihood, so since you have 3 here, the total yes is 9. Sunny, when it is sunny, then it's 3 out of 9. This one is going to be 4 out of 9. This one is going to be 2 out of 9. Where if you calculate the total, you're going to have it here. For no, don't play golf. When it is sunny, you have 2 out of 5, 0 out of 5, 3 out of 5, and the likes. If you again add across, you're going to get the same thing. This is just the procedure. Now, having done that, we're going to come back and mention something here. So we're going to discuss this special case later, but let's move on for now, hoping that we don't need it as at present. Now, having calculated just for this outlook, the same thing we have done for outlook, you have to do it for the other 4 frequency table. You do for temperature, you do for windy, you do for humidity. Just the same procedure. Now, for the sake of brevity, let us move ahead and solve a small problem here. Let's say the problem we want to solve that was the players will play if weather is sunny. So you want to check if this statement is correct, because question can come in different way. So players will play if weather is sunny. You want to check, is this correct? Or somebody asks you, calculate the probability or check if it is sunny, are they going to play or not? Now, so you can solve this by using the above discussed method of procedural probability, which we can codify in the equation we already mentioned. So here we are going to see that the probability of getting yes, if it is sunny, we have to be probability that it is sunny and yes times the probability of yes, given that it is sunny. So the first thing you have to calculate is what's the probability of sunny given that it is yes, which we already calculated there. That is 3 out of 9. That's 3 out of 9 here. So then the probability of sunny itself, that is probability of sunny itself is what? So you have to look at how many sunny cases do you have out of 14. We have 5 cases of sunny because that is 2, 3, and 2. So add it together divided by 14. Then you're going to have it. And then what is the probability of yes? You need the probability of yes, because the question is yeah, we're going to play if it is sunny. So we already assume that it is yes. That's why we're working with yes for now. If it is no, we have to calculate for no. So probability of yes is what is the total number of yes and what is the total number of samples? That's going to be 9 yes divided by the total number, which is 14. So this gives us this particular kind of values you can see here. So now the probability of yes given sunny, which already I put that in the message in the equation, is going to be a multiplication of what we've gotten, then divided by that value. So the moment we get 0.60, this is the final answer. See, we don't even need to waste our time to calculate the probability for no, because the other side is to say, okay, probability that is when it's sunny, it is no. This is the opposite. We don't need to waste time on that, because if this is 0.6, and we know the probability is maximum of 1, so the other probability is 1 minus 0.6. This is going to be 0.4. So the moment that this is higher, then we can assume that, yeah, yes, when it is sunny, then people can play golf. This is a very simple way to solve an example problem. Now we move further and also see even other, even bigger examples whereby you can be given another hypothetical questions to solve considering the
likelihood table. Now, so for the frequency table for temperature, like I mentioned, you have to bring everything on board. So from the frequency table, we move to the likelihood. The same procedure. 2, yes, is 9. 2 divided by 9, 3 divided by 9, 4 divided by 9. No is 5. So 2 divided by 5, 1 divided by 5, like that. Now, so here you can see everything is, this is why we got this. From the humidity also, you move here to get the likelihood for humidity. And the same thing goes for the windy. Now, yeah, this is for the windy. So in the same principle. So you get the likelihood. So something unique here, like I said, I'm going to come back to it later. You can see none of them is having 0 in the probability as numerator. We only had that case here. So sometimes we have to deal with it because any solution that needs this particular probability will result in 0. As we know, is 0 multiplied by anything. So it's going to affect the solution. So there's a way to deal with that. We discuss that one as we move on. Now, this is complete problem. Now let's say that this is complete. We already prepared the frequency table and the likelihood table for all. Now there's a simple question. It's saying that, okay, take for example, the same data set now is now asking us. Now, since we have prepared the likelihood table for this training data, this is training set. Don't forget, this is our training set, okay? This is training set. This is training set. So now this is testing set. They want to check if our model is correct. This is testing set. Now you need to calculate. If we now have a new sample that is rainy, mild, normal for humidity, and windy is true, should they play game? Should they go and play golf? Yes or no? See now this is a complete, you have to check rainy, mild, normal. So you have to calculate for outlook is rainy, you need temperature is mild, you need humidity is normal, and then you need windy is true. So you have to do the calculation step by step and arrive at the final result. Now, so to do this, you will need to first of all work on the likelihood of yes. See, because now you have two possibilities here. The answer, the final answer here, can either be yes or no. So what is the likelihood of yes? This is when you have probability of outlook is rainy, given yes. Probability of temperature is mild, given yes. You see, you have to select, can you pay attention to the fact that outlook has several values. However, since the sample we want to solve is given the value rainy, so you have to concentrate on that one. You have to ignore the other value that are not given for that sample. Otherwise, the computation becomes, like I said, too heavy. So that's what we're going to deal with. If outlook is rainy, what is the probability of outlook is rainy, given that it's going to be yes. Temperature mild, given yes. Humidity is normal, given yes. And also windy is true, given that the result is yes. So, and then also we're going to need to calculate the probability of yes. In the other side also, we have likelihood of no. Probability of outlook is rainy, given no, that is the answer is no. Mild, no. Normal, provided it is no. And finally, the probability of no. Because we need to calculate these two probabilities now. Then we assign it to the one that has the highest value. Now, so calculating it, so remember, this is likelihood of yes, is going to be P of outlook is yes, times P of temperature mild is yes, multiplied by the probability that humidity is normal, and then which is given that is yes, and also probability that it is windy is yes. So if you do the multiplication of the probability, remember that we already calculate all this probability. We had all this value already calculated in the likelihood table. So the final answer is going to be this. Okay. Now you have to calculate the likelihood also for no in similar pattern, which we already also had there. And then it's going to land us into this particular also value. But of course, we have to normalize. So normalize the value. P of yes is going to be, you normalize this one because you can see here that this could not be close to the probability. So we normalize it. This is going to be, so this one then divided by the addition of this and this. See, add this together, put this as the numerator, that's normalization. Put this on top and then add it together. When you normalize, we are going to arrive at this actual probability. We're going to arrive at the actual probability, which is 0.57 and 0.42. Of course, the addition of the two must always result in 1. So this tells us that the probability of yes is going to be higher. We can see that approximately 0.6, and this is approximately 0.4. Even if we don't approximate, 0.57 is far greater than 0.42. So we can conclude that this particular sample is going to be yes. See? So this is how we use Naïve Bayes to solve classification problem. It's going to successfully classify a particular sample as belonging to which of the two classes we are considering. And the classes could be more. So the more classes you have, either, yeah, if you see class 1, class 2, class 3, you just need to calculate the likelihood for each of them. And at the end of the day, do the normalization, and then you get the final probability, and then the problem is solved. So this is a very simple way, or simple example of how to use Naïve Bayes to solve a problem. I think we're going to call it a day at this point because of our time. So next week, we are going to discuss the zero frequency problem, which I mentioned earlier. There's something called the zero frequency problem. So when you have 0 out of 5, because any probability that is going to make use of that particular value will become 0. So we don't want this kind of thing. There's a way to deal with it. And then we look at other pros and cons of this method and the advantages and where we can use them. Bismillah. Thank you for listening.